Okay, so first I need to acknowledge people who did a lot of work. So Gabi, of course, is my long-term collaborator with which we've done most of the work. Then some of it was done by Ronald Cohen and Carnegie Institution, in particular the work on electron-phonon coupling that I will discuss here at length. And postdocs that were involved, mostly Ziping Kim, has done most work on iron superconductors, and Subhashish Mandal has done the work on electron-phonon and structure optimizations. So we heard a lot about Hunds Metals and Coherence-Incoherence crossover. So I can go very quickly through this because we're all familiar with it. The history is, of course, long. Zawadzki was already discussing how Hunds coupling changes atomic physics strongly. And then there was Schrieffer's work on quantum impurities in metallic hosts. And he realized that actually if you have a very large spin in a metallic host, then it's very hard to screen this large spin. This was Schrieffer's work 20 years, 30 years, no, 40 years ago, probably. Very, very long time ago. Anyway, so then when iron superconductors came around, we realized that our numerics is showing us very large mass enhancements. And we also realized that some other people didn't get that. For example, Anissimo was sending me a private email claiming that he has no mass enhancements. And then I checked his preprint and it was, he had the Hunds coupling set to 0. Okay, so I told him very quickly, well, you have to switch on Hunds coupling, otherwise you get nothing. So then we wanted to understand how come that there is this discrepancy between different calculations. And of course, the Hunds coupling was to be blamed. So then we came up with this New Journal of Physics paper in which we try to explain how Hunds coupling really rules the correlations, not Hubbard U. And the way you can understand now intuitively is that if you have several electrons in an almost degenerate set of orbitals, there can be crystal field splittings, but those crystal field splittings should be of the same order of magnitude as the Hunds coupling or smaller. Okay, then we have this physics that Hunds coupling makes high spin, prefers high spin. So the idea is that if crystal fields are not too big and you have multiple band system, then Hunds coupling will try to align spins in the same direction, and then this high spin state is very hard to screen with conduction electrons. Okay, so therefore, what happens is that the Fermi liquid scale is protracted. It means it develops at much smaller temperatures that you would expect normally, and therefore you have this region of coherence-incoherence crossover. So at high temperature, you have a very incoherent metal, which in the past was called usually local moment regime, and then you go into the coherent Fermi liquid at very low temperature. Now this, of course, Fermi liquid and crossover is actually very interesting, and lots of people have done nice work on it. But let me first introduce what we figured out back in 2008 in this New Journal of Physics that you've seen several times now. So the important point is that if you don't have Hunds coupling, then specific Kitt coefficients is more or less at the LDL level, which means that you don't have any extra mass enhancement from correlations. But when you switch on the Hunds coupling, then you see that the specific Kitt coefficient increases substantially. It goes almost exponentially here. And at the same time, the local spin susceptibility goes from a very, very small Pauli-like to something that acquires Curie-wise and then saturates eventually to Pauli-like. And resistivity, most importantly, has this coherence-incoherence crossover. So it's kind of quasi-linear at high temperature. Then it goes through this regime where it gets reduced substantially, and then it becomes Fermi liquid at low temperature. And this scale at which it becomes Fermi liquid, of course, strongly depends on the Hunds coupling and, of course, on details of the material. Now, there was related work done almost simultaneously. So our paper was put on ConMat in May 2008, and Werner and collaborators put the ConMat in June 2008 completely independently. And they have done, they studied a slightly different model. It was 3-band Hubbard model. We were studying a 5-band model, which is related to iron pnictides, but nevertheless, the physics is very similar. So the point is, what they realized is that if you have more than one electron, 1.5 or more electron in the 3 orbitals, okay, so then Hunds coupling becomes important. And more importantly, you have a large region of in phase diagram where incoherence occurs. So they call it frozen moment, but basically the one way to understand this is that you have just large region where incoherence or local moment appears, okay? Now, of course, we understand now that if we reduce the temperature sufficiently, then all this region will eventually become thermoliquid, but this will take a very, very low temperature, okay? So at high temperature, you see just as if it was frozen. So therefore the name, the frozen moment. Now, of course, there was a lot of development very quickly. Here, the review of Hunds Metals, it's a very, very nice review. So it summarized all the early work by Yernay and Antoine George. And this is really nice read that if you want to familiarize yourself, you go and read this paper. The point is that lots of those early predictions were verified by experiment, and I will try to show some of those. We've seen this resistivity in potassium iron to arsenic 2. So look at this resistivity curve here, and look at the prediction early prediction by DMFT, for example, for Hunds coupling 0.35, and you see that this at least qualitatively agrees really well. Okay, and of course experiment came after the theory. Okay, so the coherence-incoherence crossover is very clearly seen in several iron superconductors. Now, one thing that was mentioned already several times here earlier is that in iron superconductors, lots of people were claiming that they cannot be strongly correlated because they don't see Hubbard bands. There was a stream of papers claiming that non-existent Hubbard bands is a proof of weak correlations, okay? And we got puzzled with this because in DMFT, if you just increase Hunds coupling and you don't put too large Coulomb interaction, which I think is the correct regime for the Hunds metals, then you see the same, okay? So here is the calculation with dynamical mean field theory done in 2010 for iron 3D orbitals. Look at the green curve. This is with DMFT, and look at the LDA bands, the blue curve, which is without Hunds interaction. So no correlations. You have the blue curve. With correlations, you have the green curve. And then if you see this high energy spectra, you really don't see clear Hubbard bands. There are no Hubbard bands. I mean, this stuff has to do with hybridization with arsenic, okay? There's nothing to do with Hubbard bands, and there are no real Hubbard bands anywhere, okay? So in theory, we also see that there are no Hubbard bands. So the only thing that actually happens in the Hunds metals is that the low energy spectra, of course, get renormalized a lot. So the quasi-particles become much narrower. And of course, they have some structure, which we heard today in the morning, that there is this sharp needle at the beginning and then slightly broader part that corresponds to the orbital physics. So we also analyzed very early on what happens with charge excitations and spin excitations and orbital excitations. So in particular, the charge fluctuations are extremely fast. So they are completely quenched at a very, very, very high temperature. So one way to look at it is you look at the valence histogram. So you ask yourself, what's the probability that you will see that your projection of your wave function to any atomic state? So what's the overlap between the two? So in other words, how probable I can see an atom to be in N6 configuration, N5, N4, N8, and so on. And it turns out that all these valences have very, very large probability. So basically, none of them has probability more than 1%, and almost all of them are relevant. So in other words, the charge degrees of freedom are not blocked at all. That's very different than in cuprates, for example, where the double occupancy is prohibited. You can have only spin, isn't it? But here you don't have just spin. You have any possible occupancy, basically running from 4, 5, 6, 7, 8. All of those are possible, okay? So, however, what you see in this histogram is that some states are much more probable, and those are the one with high spin. So in every configuration of N, of valence, those states which have high spin are preferred, and that makes coherence scale be very small. At the same time, you can calculate orbital susceptibility, which was shown by several speakers before, and we can see that orbital fluctuations are slow, but they are still much faster than spin fluctuations. And spin fluctuations are, of course, those that are slowest, and therefore, once the spin fluctuations are become coherent, then you have a Fermi liquid. So these are the last one to quench. Okay, so and of course, this you can see how the spin fluctuations appear and become strongly enhanced at low energy. This you can see neutron scattering. Here is the example for barium 2 arsenic 2, and you can see the black dots here are experiments, and the color coding is DMFT prediction for paramagnons. So you can see so-called paramagnons, which are in very good agreement with neutron scattering. So pictorially, of course, one can think of it, of the physics in this simple way. So if you have mode physics, then when you increase the correlations, you first start to see lower and upper Hubbard band and somewhat enormous quasi-particles. That's how it usually starts from weak correlations. Then you increase correlations in mode physics, and you start to see very, very clear Hubbard bands, and then sharp quasi-particles. But in Hunds metals, it's very different. You get the sharp quasi-particles and no clear Hubbard bands. You can think of it as overlapping, or you can think of them as actually not existing. Okay, so the physics is quite different. And there are lots of consequences for this. In particular, one is that was just shown by Miao, very nicely presented results on ARPE spectra, and which agree very well with early predictions that we have this coherence-incoherence crossover. Okay, so at high temperature, as was shown in ARPEs, this XY orbital, XY band is completely non-existent. And then when you reduce the temperature, starts to show up as sharp excitation. And XZ-YZ orbital is here, and those are kind of persist to somewhat higher temperature, but still they sharpen when you go lower in temperature. So this is in very good agreement with DMFT calculations. So this is DMFT calculation, slightly bigger range of momenta. And for example, this orbital corresponds to the XY orbital here, that you see how it disappears when you increase the temperature, and this XZ-YZ orbital here persists to slightly higher temperature. So this coherence-incoherence crossover was clearly seen in experiment. And also you can, as was shown before by Miao, that actually you can also see the orbital differentiation, namely that the XY orbital is different than the XZ-YZ, and the XY orbital disappears first. Okay, so it's usually much more incoherent. Now, this special place for the XY orbital, you can see also in the Fermi surfaces. So if you look at the Fermi surface, for example, of lithium iron arsenic, as predicted by DFT and DMFT, you see they're quite different. Okay, so the difference is that this XY orbital here becomes bigger, and the XZ-YZ orbital shrinks. Okay, because it needs to satisfy the Lagrange theorem. And the way you can understand this is that XY orbital is closer to the occupation 1. Is the closest to the occupation 1. So XZ-YZ has slightly bigger occupation than XY orbital. And then when you increase Hund's coupling, it turns out that this occupation gets even closer to N is 1, okay? And that means that it's like doping holes. And doping holes means that the whole pocket for the XY orbital becomes bigger, okay? So because of this coherence-incoherence crossover, then it turns out that the Fermi surface gets changed. And by knowing how the occupation changes, how the N changes, you know that Hund's coupling would always make occupation more integer-like, okay? More integer-like means you know which orbitals are gonna increase and which orbitals are gonna shrink. Okay, so now another puzzle in the community was that the static moment in these armor superconductors is not close to 2 as expected for atomic physics, but it can be 1, can be 2, and in some materials wasn't even existing. And so the orbital moments are all over the place, no systematics, no clear way how to understand that. And there are also computing spin density wave and double spin density wave, and this looks like a mess. Now, moreover, if you do DFT calculation, for example, this is the standard GGA calculation, you will see that magnetic moments are way too big. So DFT predicts magnetic moments to be a factor of 2 too big, which is a big surprise. Why? Because it's understood that GGA is pretty good for weak itinerant magnets. For example, for BCC iron, okay, the usual iron that we have all over the place here, isn't it? That's ferromagnetic. It's understood to be weak ferromagnet, okay? And GGA predicts almost exact magnetic moments, 2.1 Bohr magneton, almost exact, okay? But in this materials, it doesn't. So the question is what's going on? And now we can say that actually LDA and GGA are pretty accurate when the entire fluctuating moment orders, Okay, why? Because it's a static theory. So you cannot have two numbers. One is fluctuating moment, one is the ordered moment. It's one and the same thing. While in dynamical mean field theory, you can distinguish between fluctuating moment and the ordered moment, and the two can be different. So now here is the calculation within dynamical mean field theory of the fluctuating moment, so this curve. And you can see the fluctuating moment has the same trend as the ordered moment within GGA. It's slightly bigger, but nevertheless with the same trend as ordered moment in GGA. So the fluctuating moment, which is like S square, okay? The S square is indeed what static theories are consistent with, okay? But this is not what the ordered moment looks like. So here in red are ordered moments by dynamical mean field theory, and you see that in different materials, half of the moment sometimes orders, sometimes even less, or almost nothing. No magnetic moment orders. So, so the idea is that above the nail temperature, of course, all the moments are fluctuating, but below the nail temperature, there is still substantial amount of the electron that still fluctuates, and only part of it orders. So that's quite amusing and unusual. And of course, to understand the entire trend the DMFT captures here, turns out that there are several things that you need to put in. So one, or we need to understand. So one is the mass enhancement, which increases through different compounds in this direction. So mass enhancement increases, therefore the fluctuating moment increases. But in some places, you have no ordered moment at all, and that's when you have competing states. So you have competing states of 1, 0, 0, 1 ordering, or 1, half, half. The two compete, and basically the ordering is very, very hard to achieve. So the ordering of magnetic moments is somewhat complicated, but nevertheless, the Hund's physics here is essential. The fact that you have fluctuating moment and ordered moment, and the two are not the same, okay? Which is hard to capture in static theories. Now, the fact that the local moment exists and that a fluctuating moment exists and at low energy and that it's big was verified by Penchek Dai very early on in 2012. So he measured neutral scattering, chi double prime of omega in integrate over omega, and he gets this mu square. And if you integrate up to 300 millieV, you get 1.8 Bohr magneton per iron as a fluctuating moment, which is very large. Now, in dynamical mean field theory, we did the calculation at the same time, and you can see the same trend and more or less the same number. So if you integrate up to 300 millieV, we also get of the order of 1.7 Bohr magneton, and if we integrate to infinity, we get 2.5 Bohr magneton. So there is still fluctuating moment, which is hard to measure in neutrons. But the point is, these are very large numbers. So there's a lot of fluctuating moment at low energy. Now, the title of the talk is about electron-phonon coupling and the structure. The question is whether these fluctuating moments have anything to do with structure or electron-phonon coupling. Do they change that or they don't? Is the lattice affected in any way or not? And the answer is yes, it is affected in several ways, and let me try to walk you through. So of course, the electron-phonon coupling in this iron superconductors is too weak to explain superconductivity by itself. Of course, we believe that spin fluctuations are essential, but nevertheless, phonons can boost TC, and at least as we showed in previous talk, in iron selenide, that's most of people believe that phonons do play an important role, and our calculation is for iron selenide. So what is the electron-phonon coupling? The electron-phonon coupling is when you move atoms in a particular direction of the phonon mode, then you observe how much the band structure or the ARPES changes, or how the bands move. So the bands will change when you change, for example, selenium here in the direction of the movement of outer plane. Okay, so this particular A1G mode. So we found that actually this A1G mode, which has to do with the proximity of selenium to iron. So how close selenium and iron planes are. So this particular A1G mode is the most important and changes a lot when you include correlations or don't. Okay, that's the most important mode, it has the biggest effect. Now, but before we look at the electron-phonon coupling, we need to first have a reasonable structure, okay? And it turns out that if you have just a non-magnetic DFT, then the structure is actually pretty bad. So yeah, non-magnetic LDA, for example. Turns out that this position of selenium above iron is way too close. So it's 0.23 rather than 0.27. That's a huge difference. Now, what's the problem? The problem is the selenium is too close to iron, okay? Why is that? Because DFT overbinds. So when DFT overbinds, it wants these atoms to come very close, okay? And basically, they are not sensitive to so the bands are not very sensitive to the seleniums, they just become very close and they completely bind, okay? However, when you go to better theory like GGA, you already get a better agreement with the experiment. Then if you go to magnetic magnetic GGA, it's even better. And finally, DMFT is very, very close to the experiment. So what happens is that if you allow correlations on iron, then iron tries to be bigger. The idea is that correlated ions want to be bigger, and they push away selenium. Okay, so once you have this good agreement with experiment for the structure, then you can think of electron-phonon coupling. So what we do here is we displace selenium a little bit out of the equilibrium, and we ask ourselves, how does the band structure change? Here's the band structure. And within LDA, the band structure change is very small, while DMFT bands or DMFT spectra changes much more, way more, factor of 10 sometimes, okay? So here is one example, which factor of 3, but I will show later on the plot, it can change much more, okay? So here is the so-called deformation potential, which is the change of the band energy divided by the displacement of the ion, selenium ion, as a function of pressure. And you see that it has behavior more or less reminiscent of the TC in iron selenide. So it increases up to some pressure of 2 gigapascal, and then it starts to decrease substantially. So that gives you a hint that maybe superconductivity is enhanced by electron-phonon coupling. But most importantly, we have now finally a possibility of predicting the numbers. And the question is whether they are in good agreement in experiment or not. So this is the DFT optimized position for selenium 0.245, in DMFT 0.27, and in experiment it was known that it's close to 0.27. So this we actually didn't predict this, we just realized that it works. Now the phonon frequency is 5.7, and experimentally it wasn't known back in 2014. And electron-phonon coupling in DFT is minus 1.6, in DMFT is between minus 10.3 to 13.4, depending on where in the Fermi surface you are, and experimentally it wasn't known. And we couldn't get this published in PRL, it was only PRB. Similar to the other New Journal of Physics, which is supposed to be Nature Physics, it wasn't Nature Physics, which is New Journal of Physics, after a year and a half of fight with the referees. But this one was PRB because that looked disastrous for referees, because it can't happen. Okay, so nevertheless, there was this pioneering experiments from Stanford group in which, so this was by Tom Devereaux and Zheng Shen, that actually measured the electron-phonon coupling directly. And I think this is pioneering in the sense that I have never heard before of this being possible, okay? But they can measure electron-phonon coupling directly in their new design of the experiment. So what they do, well, first, their number that they got is minus 13, and look, the prediction is more or less at the same range. So minus 10.3 to minus 13.4. So almost perfectly in agreement with prediction. And prediction was at least 4, 5, 6, 7, 3 years before. Okay, now, how do they measure this? Well, they sent 2 pulses at the same time to the sample. One is used to measure Bragg peaks. This is X-ray for the Bragg peaks. And then another one is UV light that measures the ARPIS at the same time. And they're both pulses in the sense that they create an oscillatory signal, and then they measure these oscillations, okay? And when they see that the Bragg peak is changing with time, basically the intensity of the Bragg peak changes, isn't it? This is intensity of the Bragg peak determines the internal positions of ions. And because the intensity of the Bragg peak changes with time, they can figure out exactly how much selenium moves with time as a function of time, isn't it? So this is the movement of selenium as a function of time after the pulse, okay? At the same time, they do ARPES on exactly the same sample at exactly the same time. And then they see that the bands change with exactly the same frequency. So this is the frequency of the XZYZ orbital and this frequency of the Z-square orbital. So how does it change as a function of time? And now if you take the ratio of this change of the energy of the bands divided by the change of the selenium position, that's exactly electron-phonon coupling. Okay, that's exactly what we calculate. It's called deformation potential, and they can give you this number, minus 13. Okay, so perfect agreement with experiment and measured more or less the same as being calculated. So beautiful, beautiful work, and very nice demonstration that this DMFT does have some checks with reality. Okay, so the other thing which was kind of important is, of course, spin susceptibility. So spin susceptibility is measured with neutrons, and as we said, spin susceptibility is strongly enhanced at low energy because of this Hundsness. And so we would like to compare this to experiments, experiments if we can predict with DMFT good spin susceptibility. The way we do it is, of course, the irreducible particle Hall vortex is calculated directly from the impurity. So the vortex corrections are included, very important, but they are local, so we can calculate by impurity. And then we add the Green's functions here, the both LDF plus DFT Green's functions, and we calculate this beta-Salpeter equation. And if we do that, then here are the results. So warriors are on superconductors, predictions by DMFT for neutron scattering dispersion. And you can see these are all paramagnons, so we can predict paramagnons. And in some materials, there was also experiment, black dots here, and they agree pretty well with the theory. In some materials, there wasn't an experiment yet. Iron selenite, it came later, but it agrees with prediction pretty well. So these trends are pretty well captured. But what's more important for the understanding of superconductivity is that in all iron superconductors, where the TC is high, we always see very sharp pi00 pi excitation. So this is at low energy, at 5 millieV, as a function of Kx and Ky. If they have pi00 pi excitations, then they have high TC. If they don't have a high TC. We checked for several materials, they don't have high TC, and then they don't have these excitations. So this excitation actually gives you, we can calculate also the particle-particle response, which is a superconducting instability. And in this superconducting instability, as we show in the previous talk, has this simple form, cosine Kx times cosine Ky. The reason for this cosine Kx times cosine Ky is because you have this pi00 pi excitations, spin excitations, okay? So pi00 pi excitations gives you this prefactor, cosine Kx times cosine Ky, but then you have because we have three orbitals, xz, yz, and xy, you have a freedom of putting a face on each orbital, okay? Now, if you put the same face on all orbitals, you're gonna get conventional S plus minus. So all orbitals have the same face, let's say plus, then you have just cosine Kx times cosine Ky. This is conventional S plus minus, okay? No, nothing so spectacular or interesting. However, now that you have orbital physics, not band physics, not simple band superconductivity in band picture, but in orbital picture, what you can do is you can flip the sign on XY orbital, and it costs you almost nothing. So in terms of the eigenvector, value of the eigenvector, it's almost the same. So in terms of this outside pocket here is XY pocket, and here outside pocket is also XY pocket. So if you flip the sign for the XY orbital, you will see that the outside band becomes now positive and inside negative, and here the outside negative and inside positive, okay? So that's what we call orbital antiphase. So by just flipping the sign on one orbital, like XY orbital, you can go for conventional S plus minus for orbital antiphase S plus minus, and you can also flip the sign between XZ and YZ orbital, and then you get a D wave pairing. Now, they are all competing in our theory. It's hard to know which one exactly wins in which situation, but nevertheless, the orbital antiphase is very interesting because it's different than what you get in recoupling. And at least there are some reports from Honding's group claiming that this is probably the best pairing symmetry for our superconductors. It would also explain why in iron selenite you can have only electron pockets and you still have superconductivity, okay? Because the electron pockets have a different sign on the two sheets when they only survive, okay? So thank you very much for bearing with me.
Other questions? Yes, please. Let's have a question. You say that electron-phonon couplings enhancing the TC would expect some isotope effect in PPS seems inferior to other experiments.
Okay, that's a very good question. Well,
can you repeat the question?
Yeah, so the question is that if electron-phonon coupling plays any role in it, even if it's subleading, doesn't it? Then you would expect isotope effect, doesn't it? And the question is whether isotope effect was seen or not. Now I'm gonna try to be vague here because I don't remember the experiments. As far as I remember, there are several experiments which do show isotope effect, okay? Now I cannot quote exactly which experiments, but I remember in the early works, there was a lot of people who were claiming that it's phonon driven only because they saw an isotope effect, okay? So I believe that electron-phonon coupling do plays a role. I mean, actually, even in cuprates, a lot of people believe that phonons do play some role, doesn't it? Not the leading role, but sub-leading role. So they're important to understand really the value of the TC, okay? But isotope effect was definitely seen. I can't recall the experiments. Yeah.
Just to clarify, when you look at the enhancement of the electron-phonon coupling by itself, this is due to the change in the cell energy, because you cannot explain by just non-linearity of the cell.
No. No.
Just repeat
So,
the question.
it's the origin of the electron-phonon coupling. So is it this due to the self-energy, due to spin and orbital fluctuations, or it comes from non-linearity of the phonons, I guess.
The real part of the self-energy, actually, if the self-energy does not change when this case happens, you will still get a slightly different electron-phonon coupling without the energy of bandits.
Yeah, actually it's an extra question. The two are more or less convoluted, and I don't know how would you decouple the two. I definitely assign this to basically spin and orbital fluctuations, in particular spin fluctuations, which are the strongest. But can I distinguish whether this is because of the real part of the self-energy, imaginary part?
Kristjan, a question from the audience.
Question from the audience. Forces are computed from Hellman-Feynman theorem. Is this still valid in this regime?
No, they're not computed with Hellman-Feynman theorem. That's not true. So the forces are computed. There are Haule forces, and very important Haule forces, which we actually implemented in 2016. Actually, to be honest, all this work on electron-phonon coupling was done even before the forces were implemented by finite differences, which is much, much harder to do, okay? But now this is so much easier because the forces are implemented and they're not Hellman-Feynman. Actually, they are so-called Haule corrections are very important. Yes?
So come back to the origin of the electron-phonon coupling. How much of it is in the Young-Teller effect? In other words, that if you displace the selenium atom from the iron, you're changing relative orbital energies for self-existent relative orbital energies.
Okay, it's another excellent question. So
can you repeat it?
So the question is that whether this change in the electron-phonon coupling has to do with Young-Teller physics, in which the orbital occupation would be the driving primarily force of the change versus let's say spin fluctuations or orbital fluctuations. So it's an excellent question. And as far as I remember, now here I'm not absolutely sure, we need to look at the data, but as far as I remember, the change of the orbital occupations was relatively minuscule. Okay. Now, of course, you can say that we're looking at the linear response, so we don't expect the big numbers anyway. So one would need to do this very, very careful analysis to say whether it's true or not true. Okay. So I cannot prove or disprove on the spot. My feeling is that it's not.
But usually DMFT does a fairly good job with Young-Teller systems. No. That's the whole point. Of course.
Kenner has that, yeah. No, that's true.
The question is whether it's some electron-phonon lattice coupling or whether it's
No. It has to do with the fact that actually, even if occupation change for, let's say, 0.1, that's a big effect in the linear response. In the linear response case. So what we would need to do is only do the calculation and force the orbital occupation to not change and see if we get the same effect or not. And the answer to this question is I don't know. Thank you.
Kristjan, one more question from your next.
Okay, yes, Janne?
Kristjan, very nice talk. I have a question about, I mean, how many systems did you actually look at in terms of electron-phonon coupling in the DMFT? Is this like general phenomenology or it's very specific to the things you looked at? But I guess the thing is quite unexplored, no?
Very unexplored. Now, Subhashish Mandal, who did this work, is actually now postdoc at Rutgers, and he looked at recently on, I don't know, 30 or 40 of them. This is non-published. He's still preparing the work. So we looked at several now, not just one. And this is going to be hopefully in NIST database. So we are preparing NIST database in which we are going to store all these calculations, hopefully soon.
When you are talking about 30 or 40 materials, you mean from these iron materials?
Yes.
Oh, okay.
Iron superconductors. So we ran through those that we calculated mass enhancements before.
Yeah, but other compounds would be interesting too, I guess, no?
Yeah, absolutely. I mean, iron selenium was the most hot, so therefore we did this for this. It was hard calculation anyway, so.
The discussion further afterwards, because we're running 5 minutes late now. Right. Unless there's something more. No, I don't think. Okay.
So let's thank Kristjan again.